Alright, hello class. Welcome to section 2.5 where we're talking about limits at infinity. So limits at infinity are basically limits where we look at f where x goes to infinity or x goes to negative infinity. In other words, it basically helps us describe the behavior of a function f of x as x increases without bound or decreases without bound. Okay, so I'll add that, or decreases without bound. Okay, in your pre-calculus class or your algebra class, this may have been called the left and right end behavior of a function. Basically, what is the function doing as x goes all the way out to the right? Okay, and what is f of x doing as x goes all the way out to the left? So a prime example of this would be something like 1 over x, okay, or 1 over x squared, like this graph shows here. Okay, so here's the graph of 1 over x, okay, and as x increases without bound, so in other words, as x goes out to infinity, we see that the function itself, right, as we map up, it's kind of harder to see, but as it goes out, it's getting closer and closer to 0. Okay. And as we let x go out to the left, to negative infinity, right, we also see that the function is getting closer and closer to this line at 0, right, y equals 0. So it's kind of leveling off. This is like a leveling off place. Okay, so as we see here that the limit as x goes to infinity of 1 over x is equal to 0, as is the limit as x goes to negative infinity of 1 over x. Right? It's going to 0 on both sides. Okay. On the other hand, if we look at 1 over x squared, it actually goes to 0 faster, right? As x goes to the right, increases without bound, we see that the graph itself is swooping down to 0 way faster than it did over here. Here's the 0 line. And, okay, when it goes out to the left, decreases without bound, it's behaving the same way. Both sides it's going to 0. Here it's both coming down to 0 from the positive side, whereas on this over here, on the right, it's coming from the positive side, positive y's, here it's negative y's. Okay. So the limit as x goes to infinity of 1 over x squared is equal to 0, as is the limit as x goes to negative infinity of 1 over x squared. Okay, so I have a table here that shows this same idea. Basically, as my x's get really large, okay, my 1 over x is getting very large, or excuse me, getting very small, getting very close to 0. And if you think about it, like when x is 100 or 1,000, this is 1 over 1,000. It's a really small number, right? Really close to 0. And 1 over x squared, well, 1 over 1,000 squared, that's minuscule, right? As is 1 over x cubed. If I take 1 over 1,000 cubed, I mean, we're talking about a super tiny number. And if we look at, say, negative 1,000, we're getting similar results, right? Because the only difference is that 1 over x is going to give us a negative number, whereas 1 over x squared will give us positive numbers always, right? Because that squared will cancel out any negatives. 1 over x cubed is giving us a negative, but all these cases are still going to 0. In fact, what we can say is that the limit as x goes to either plus or minus infinity, either side, it doesn't matter, of 1 over x to any positive power, we should say, got to be careful there, is going to go to 0. Okay. So this is our first rule, basically. And I'm not going to write all the properties here, right? This can't be like the square root of x if you're letting x go to negative infinity, because you can't put negatives in. But, you know, I'm leaving that up to you to fill in the blanks there when this is going to be possible and whatnot. But we definitely would need p, the power, to be greater than 0. Right? Negatives, if it was negative, we just flip it right back up, and it's not a 1 over kind of situation anymore. All right? So that's basically our first property. All right, the next one, okay, is dealing with, let's say now instead of 1 over x or 1 over x squared, we have just x, or x squared. All right, and I hope it should be fairly obvious if I have the limit as x goes to infinity of x, where do you think that limit's going to go, right? X is going to infinity, so x goes to, well, I hope you guess infinity, right? Because as x increases without bound, x, of course, increases without bound. And how about the limit as x goes to negative infinity of x? Well, obviously, that's negative infinity, okay? Pretty simple. How about the limit as x goes to infinity of x squared? Well, also should be pretty clear, that's going to be infinity, right? As x goes to infinity, now we're squaring it. So say if x is 10 million, x squared will give us 10 million squared. It's going to go to infinity faster than x, but it still goes to infinity. And how about the limit as x goes to negative infinity of x squared? Well, that x squared, the squared term, is going to cancel out the negative sign, right? So this also goes to positive infinity, okay? And then, you know, we can keep this going. The limit as x goes to infinity of x cubed is infinity, whereas the limit as x goes to negative infinity of x cubed is negative infinity, since the negatives will be preserved with our x cubed term. Okay, and any even power is going to get rid of any of our negative signs, whereas any odd powers are going to preserve negative signs. And again, constants aren't really going to affect much, except, let's say I have the limit as x goes to infinity of negative 2x cubed. Well, where will that go? Well, the x cubed is going to positive infinity, but we're multiplying by a negative number, so that negative number is going to affect things, right? It's going to take all those positive values we have, make them all negative. So this is going to be negative infinity. Now, there's some people who will fuss at you for doing this, but I actually don't mind that much. If you were to put negative 2 times infinity here as part of your answer, if that helped you, right? And then you say, oh, negative 2 times infinity, that's negative infinity. If you need to write that to help you out, that's totally okay with me. Okay, that's not a problem. And then if I have the limit as x goes to negative infinity of x cubed, or not x cubed, excuse me, negative 2x cubed. Well, x going to negative infinity, that means x cubed is going to negative infinity because x cubed preserves negative signs, but now we're multiplying by negative 2, which makes it a negative negative. That's going to be positive infinity. Right, again, in parentheses, if you need to write negative 2 times negative infinity, which is equal to positive infinity, totally okay. All right, totally okay. So this should be, I mean, pretty simple, I hope. These infinity limits are pretty straightforward, I think, right? If x is going to infinity, what is x to the 5th doing? Well, clearly it's going to infinity. The only thing that can really mess up things is that coefficient on the front, right? That constant on the front. The only thing that really needs to be talked about now is what happens if it's not just x to the third or x to the fifth. What if it's something like, I don't know, let's say the limit as x goes to infinity of, let's say x to the fifth minus 30x cubed, I don't know, minus 10x squared minus 100x. Okay. Now here, okay, so we know that x to the fifth goes to infinity, right, as x goes to infinity. But negative 30x squared, that goes to negative infinity. And negative 10x squared, that also goes to negative infinity as x goes to infinity. And negative 100x as x goes to infinity goes to negative infinity. Okay? Now, what is going on here? Does this thing go to negative infinity? Does it go to positive infinity? Does it go to 0? Right? Because what we essentially have is like an infinity minus some other infinities. So it might, some people might think, well, don't these infinities cancel? And then we're left with these two, so it'd be negative infinity. Well, the answer is actually no. What I'm going to say here, this is my claim or proposition, is that this thing is actually equal to the limit as x goes to infinity of x to the fifth. Right? This thing is equal to, okay, the leading term of what we started with. Okay, so the leading term of this guy, which means the term with the highest power of x. Okay, and that's going to be positive infinity. So note, this is a big deal, right? Infinity minus infinity, that does not equal 0. In fact, this is what we call an indeterminate form. Let me write that down, an indeterminate form, because infinity minus infinity, well, it might be 0, it might be infinity, it might be negative infinity, just depending on the outcome. For example, if we talk about the leading term idea, here's another case where if I had the limit as x goes to infinity of 100x minus x to the fifth, this is positive infinity, this is minus infinity, but if that leading term idea is true, then the limit as x goes to infinity of negative x to the fifth will be negative infinity. Okay? It changes. Right? So that's why we call infinity minus infinity an indeterminate form. So let me kind of verify this claim, verify this proposition that it is the leading term, okay, that really matters. And where the idea comes from is, remember, we're letting x go to infinity, right? So say close to 0, all these negatives are going to have a huge effect and like change things and bring x to the fifth down and probably have, cause some really wild behavior. But we're talking about x going all the way to the right, right? We're talking like x equals 10 million, 10 billion. And eventually, right, 10 billion to the fifth is going to completely dwarf everything else we see here, right? It's going to completely destroy negative 30x cubed, right? Okay. I can even show you if we use a calculator and I say, let's say 1,000 to the fifth. Okay, that's 1 e to the 15th, right? So that's For those of you who don't know what that means, that's 1 times 10 to the 15th power. That's a huge number. But if I do negative 30 times 1,000 cubed, okay, that's negative 3 times 10 to the 10th power. Now you might think that, well, those are pretty close, but this guy has 15 zeros after it, whereas this guy has 10. Okay. Might not seem a lot, but in the grand scheme of things, and that's just 1,000, okay? Imagine what happens when we get up to like 10 million. The other thing I want to mention is eventually, right? And this comes from the claim that as the limit as x goes to infinity, this whole thing, its limit is actually going to equal the limit as x goes to infinity of just the leading term. Okay? So, to kind of show this, I'm actually going to show you some graphs. So here I went to my y equals, and I'm going to show you x to the 5th, and then x to the 5th minus 30x cubed minus 10x squared minus 100x, exactly what we have here. Okay, I'm going to show you, different windows what's going on. So we're going to start, say, from 0 to 5, and I'm using zoom 0, which is fit. Now, this is a very useful thing because zoom fit picks the y values that will work the best. Okay. So it's working. Right, sorry about that, camera issues. Anyway, the functions graph, here is the first one, x to the 5th. And then here's the second one, the x to the 5th minus 30x, the crazy one we are dealing with. As you can see, this was, what was the window again? 0 to 5 on the x, right? So 0 to 5, you can see there's not much to see at the moment. But x to the 5th is always going to be positive when x is positive, but we see here that these negative values of, the negative 30x cubed, the negative 10x squared, the negative 100x are actually pulling the function down into the negatives at this point, right? So let's take this a little further. Let's go to, I don't know, let's go all the way up to 20, right? 0 to 20, and zoom 0, which gives us zoom fit. Okay, and let it think a little while. Okay, and here we go, plotting x to the 5th, and then you can see there isn't much of a difference between x to the 5th and our crazy function we're looking at, right? So, and look at this, it's below that first one. Those minus things, right, are actually pulling the graph down a little bit, but not by a whole lot. I don't know if you can even see the difference on YouTube or not, but there's a very small difference. And if I was to go to something like 0 to 100, and let it graph. Here's x to the 5th, and now it's graphing the second function, and I can't tell a difference at all. Okay, I didn't see it graph the second function, right? So as you can see, eventually, and this was, as x got to about 100, right? So at about 100, right, these two functions are really close together. And remember, the limits are all about things being close, really close together. So as we saw graphically, that basically x, can't even see that, but x to the 5th minus 30x cubed minus 10x squared minus 100x basically goes to x to the 5th as x goes to infinity. Okay, so this will help us, say, find limits, at infinity for various different functions. They could be crazy things, but say the limit as x goes to infinity of x to the 10th plus 3x squared minus 100x to the 9th plus 33. Well, doesn't matter. This limit is going to be the limit as x goes to infinity of x to the 10th, which is positive infinity. Okay, I do kind of want to see this early work, but basically you're just looking at the highest power of x that you see. Okay, so for example, let's say I have the limit as x goes to negative infinity of, let's say, negative 3x to the 9th plus 33x to the 7th minus 16x plus 1000. Okay, well, the only thing that really matters, and keep in mind this is only true for limits at infinity, okay, or negative infinity. This is really the only thing that matters. Okay, this limit is going to be equal to the limit as x goes to negative infinity of negative 3x to the 9th, the highest power of x that we see. Okay. All right, so x to the 9th, that's an odd power of x, so it will actually preserve the negative signs, meaning that that goes to negative infinity, but we're multiplying by a negative number, so it makes this thing positive infinity. Okay, and you can graph this guy to see. You can always graph these with your calculator to kind of see where they're going. There's nothing wrong with that in these cases, because you're really just looking at how the function behaves. Right? Okay, how about the limit as x goes to infinity of 3 plus 1 over x squared plus 16 over x to the 10th. Oh, this one's a little different. This is going back to the things we saw before. Remember, 1 over x to a power, the limit as x goes to infinity, these are going to go to 0. Okay, and then this should just be equal to the limit as x goes to infinity of 3. And we haven't really talked about the limit of a constant, but think about it. Does x affect 3 at all? No. So, whoops. So the limit of a constant is typically x itself. Okay, so we can write that down here. This is a rule that the limit as x goes to some value a or infinity, doesn't really matter, of a constant is pretty much just a constant because the x is not affecting anything there, right? Okay. Okay, so the next thing to talk about real quick is in behavior for e to the x and the natural log of x. Okay. Basically what we have is that the limit as x goes to infinity of e to the x is infinity, and the limit as x goes to negative infinity of e to the x is 0. Right, and if you remember what e to the x looks like, here it is. It's got a horizontal asymptote over here on the left, and it shoots up to infinity on the right. Okay. And for e to the negative x, well, you can get those just by remembering that e to the negative x is 1 over e to the x. So as x goes to infinity, well, since e to the x goes to infinity in that case, we'll have 1 over that, which goes to 0. And for the limit as x goes to negative infinity of e to the negative x, well, that's going to be putting negatives in there, so it flips it around. Okay. And then the limit as x goes to 0 from the right of the natural log of x is negative infinity. You can see that from the graph, right, as x goes to 0 from the right. And the limit as x goes to infinity of the natural log of x is infinity. Okay. So some things to keep in mind. Don't ever write these in a formal setting, but things to help you keep things straight is, remember that 1 over infinity is 0, and that's plus or minus infinity, actually. Okay. E to the infinity is infinity. E to the negative infinity is 0. You know, the natural log of infinity is infinity, and the natural log of 0 coming from the right. Remember, the natural log of 0 is undefined, but natural log of 0 coming from the right, that limit is negative infinity. Okay, you should never write these, but I think these help, you know, kind of get them in your head a little bit, right? Infinity to positive power is infinity. Okay. So that should help a little bit. So when we, you know, throw all these together, if we have like the limit as x goes to infinity of 6 plus 1 over x squared plus x to the negative 5 plus 3e to the negative x. Well, 1 over x squared as x goes to infinity. Well, we know that just from what we've talked about. That goes to 0. X to the negative 5, well, that's the same thing as 1 over x to the 5th, just using, you know, our algebra. And so we know that that goes to 0. And then 3e to the negative x, well, of course, we know from what we just talked about that that is going to go to 0, but also you could say that that is 3 over e to the x, right? And that would be as x goes to infinity, 3 over infinity, which is 0. So all these go to 0, and so the whole shebang ends up being 6, right? So the limit as x goes to infinity of 6 is simply 6. All right, I mentioned that word asymptote, and I want to give the official definition of a horizontal asymptote now. Remember, with vertical asymptotes, we use limits to give us the new definition of that. That was if we took the limit of a function at some value, say a, and we got a blow-up. We got that limit equaling plus or minus infinity. That gave us a vertical asymptote at that value, say x equals a. Here, it's kind of flipped. If the limit as x goes to plus or minus infinity of f of x equals c, some number, then, some finite number, I should say, then f of x has a horizontal asymptote at y equals c. And just like the other ones, this is actually how we write it. And this gives us the new definition of how to, or new way to talk about asymptotes. Right? So basically, yeah, if you have the function leveling off, so an example of an asymptote, you know, you've seen it before in your pre-calc class, but if the function levels off, right? So say this is f of x, this is some function, and we see that the limit as x goes to infinity of f of x equals L, right? It levels off. And it doesn't have to be the same on both sides. You see here, and with e to the x, if you remember, right, the graph of e to the x here, it has an asymptote on one side, but not on the other. This graph I just drew has an asymptote on either side. And it's definitely possible to have two different asymptotes on either side. Okay, so an example of a function that has two different asymptotes on each side is tan inverse, or arctan. As x goes to the right, tan inverse gets closer and closer to pi over 2, while on the left it goes to negative pi over 2. So we could say that the limit as x goes to infinity of tan inverse of x is pi over 2, whereas the limit as x goes to negative infinity of tan inverse x is negative pi over 2. Right, so they don't have to be the same on either side. It can differ. So a function can have two horizontal asymptotes. It can't have any more than two. All right, it might not have either, because it could blow up on both sides, for example. Okay, so the last thing to really talk about in this section is when we have, say, fractions of things, and we're looking at the limit as x goes to infinity. Okay, so the trick here is, right, from the leading term idea that we have, I know this x to the fifth is going to take over, and really this is pretty easy because it's infinity plus 15. So infinity plus infinity is definitely, an infinity thing. But here in the denominator, x cubed is the greatest power of x, so we know that the denominator is also going to infinity. And this is an indeterminate form, that is the infinity over infinity case, and that can be plus or minus, it doesn't really matter which. Where this is indeterminate because, well, basically, it's kind of spoiler alert, but if the top goes to infinity faster than the bottom, then the whole thing will go to infinity, whereas if the denominator is going to infinity faster, it should make the whole thing go to 0. And the other possibility is that they go to infinity at the same rate, right? So they might actually cancel each other out. Now, we want to show this, and intuitively we guess that, right? I guess, oh, x to the fifth, that goes to infinity faster than x cubed does, right? It's the one that will take over, so I suspect the whole thing should probably go to infinity. Let's actually show why. Let's show how we do this and the method of doing these problems. And you might think, well, why do we have to actually go through this process if, we can intuitively just guess? And we'll hit an example here in a bit that really shows why we need to worry about this, just because it can get a little hairy if we're not careful. Okay. So what we're going to do is we divide everything by the highest power of x in the denominator. So the highest x power in the denominator. I often write it like this: 1 over x cubed over 1 over x cubed. So the highest power of x, the highest x term in the denominator is x cubed. Or I just jump straight to this and just say, all right, this is going to be the limit as x goes to infinity of x to the fifth over x cubed plus 13x squared over x cubed plus 15 over x cubed all over, let me move this up, x cubed over x cubed plus 33x squared over x cubed plus 6x over x cubed. Now you might be thinking, well, what the hell? This just made things worse. Well, actually, once we simplify this, we've actually made things better. Okay, so let's take a look at that. Let's simplify. Okay, so simplifying, we will get that this is the limit as x goes to infinity of x to the 5th over x cubed will give us x squared. X squared over x cubed, that will give us 13 over x, and of course 15 over x cubed just stays 15 over x cubed. In the denominator we get 1, plus 33 over x, right, since x squared over x cubed just gives us over x, plus 6 over x squared. Now when we look at this, what we've basically done is simplified things such that everything is either going to 0, is a constant, or we have things going to infinity. This actually simplifies a lot because as x goes to infinity, these guys go to 0. This is 1, and x squared goes to infinity. So the whole thing is basically going to, I'm just going to write it like this, infinity plus 0 over 1 plus 0 plus 0, which is infinity over 1, so that's infinity. And that's actually what we suspected, right? We suspected that, well, the numerator is going to go to infinity faster than the denominator, therefore the whole thing should probably go to infinity. Let's look at another example, where maybe it has the opposite behavior going on. Okay, so for this one, we have the limit as x goes to negative infinity, so this method will work for that case as well. X to the 7th plus 16x to the 5th plus 70 all over 17x to the 10th minus 3x to the 4th plus x cubed. So remember, we divide everything by the highest power of x. We don't have to take the constant along too, just the highest power of x. Right? So limit as x goes to negative infinity, x to the 7th over x to the 10th plus 16x to the 5th over x to the 10th plus 70 over x to the 10th all over 17x to the 10th over x to the 10th minus 3x to the 4th over x to the 10th plus x cubed over x to the 10th. Now, as you can see, this step is really tedious to write. You can actually skip to this very next step where you start simplifying things. If you want to do all this stuff in your head, I don't blame you if that's what you want to do, right? Because this will cancel to be, or x to the 7th over x to the 10th will cancel to be 1 over x cubed. This will cancel to be 16 over x to the 5th, and the 70 over x to the 10th just stays as is. Then we get, well, these cancel and we just get 17. Okay, right, minus, this will be 3 over x to the 6th plus 1 over x to the 7th. Okay. So, since the x is going to negative infinity, all of these x's in the denominator here are actually going to go to 0, right? 1 over x cubed goes to 0, 16 over x to the 5th goes to 0, 70 over x to the 10th goes to 0, negative 3 over x to the 6th goes to 0. 1 over x to the 7th goes to 0. So the whole thing ends up going to 0 plus 0 plus 0. Again, you don't have to write this step. I'm just being very explicit here. What we really have is 0 over 17, which is 0, right? Which might be what you suspect looking at this, because I have that, well, the highest power of x is in the denominator. X to the 10th goes to infinity much faster than x to the 7th. Okay? Whether it's plus or minus infinity, it doesn't really matter here. Yeah, so, you know, the denominator goes to infinity much faster, and so this whole thing is basically going to, you know, something over infinity, which brings the whole thing to 0. Okay, for the next example, I'm going to look at the limit as x goes to infinity of 2x to the 5th minus 140x cubed plus x squared all over 3x to the 5th plus 50x squared minus 10. All right, so here the highest power of x is both in the numerator and the denominator. Okay, so what happens there? All right, they're both going to infinity about just as fast. So let's see. Let's use our method here. Right, we're going to divide everything by x to the 5th. Okay, so we'll get the limit as x goes to infinity of 2x to the 5th over x to the 5th minus 140x cubed over x to the 5th plus x squared over x to the 5th all over 3x to the 5th over x to the 5th plus 50x squared over x to the 5th minus minus 10 over x to the 5th. Okay. And again, often I skip straight to this step, which is, well, those two are just going to cancel out directly to give us 2 minus 140 over x squared plus 1 over x cubed all over 3 plus 50 over x cubed minus 10 over x to the 5th. Right, and again, x is going to infinity, so everything with x's in the denominator there goes to 0. And so we're left with, well, 2 minus 0 plus 0 over 3 plus 0 minus 0. So this is 2/3. Okay. So this is why the infinity over infinity case is an indeterminate form, right? Because sometimes it's going to give us infinity, sometimes it's going to give us 0, and sometimes it's going to give us a constant. Same with the 0 over 0 case. You can set 0 over 0 up to either give you 0, a constant, or infinity if you write things correctly. Okay? So that's what we see here. When the highest powers of x match, we're going to get a constant, and it's specifically going to be the coefficients, the fraction of the coefficients. Now, for right now, test 1, don't just write the answer. Right? You can look at this to know what your answer will be, but I want to actually see some work here. Right? I want to see what you're doing. I want to make sure you get this technique down, because there are cases where it's actually really going to help you to know, okay, this particular technique. Okay, that's pretty much what I wanted to talk about in this particular section. The only other thing really left to mention, okay, is you aren't always going to have a value for an infinite limit. So for example, if you consider a trig function like sine of x, right, it looks like this and just continues on with this behavior forever and ever. Forgive my really crummy graph here, and on the other side too. Okay. So the limit as x goes to infinity of sine x, well, is it shooting off to infinity or negative infinity? No. Is it leveling off to a nice, value that we might like? No. It's not doing either. So actually this does not exist. So for functions that oscillate over time, don't, ever level out as x goes to infinity or negative infinity, they just don't have a limit, right? They don't have a limit at infinity. Okay. All right, so that's pretty much it for 2.5.